Yo, VIP. Let's kick it.
Hello once again, AP Calculus BC students. Mr. Record from Avon High School here. We're taking a look at another video in our long series of videos dealing with vector value functions and particularly applications of those kinds of vectors. We have a motion application here once again that kind of can be sort of somewhat related to, if you ever happen to be driving around and see fire trucks kind of huddled around a home, unfortunately, that has caught a fire. Perhaps some of the things that are discussed in this problem could be on the concerns of firefighters. So let's read through the question. It says that water from a fire hose is discharged at a maximum rate of 80 feet per second. Firefighters can only get 25 feet from this burning building. And they're going to shoot the water from their hose, and they're going to do so angling the hoses at 45 degrees to the ground. Our first part of the question asks, what is the maximum height that the water can reach? And then later we'll decide that if the building did unfortunately completely burn down and the firemen were shooting the water just on the wreckage, how far into that wreckage could the water reach? And that is assume that they're still using that same angle of 45 and they're 25 feet from the beginning of the wreckage, so of the burning building. So what we need to do for this part A is kind of develop a plan of attack, and we as with most of our vector problems, we're going to kind of think about a position vector to get things started. And we use R a lot of times in my classes. S will work just as fine to depict this position vector. And as with all vector motion problems, you have your I component and your J component. And we can kind of sometimes think of the I component as being constructed with some quantity expression x of t, like a distance in terms of x, and our J component will have this sort of vertical component y of t. Now, specific to this problem, using some of the information that was gleaned in some other videos that I've done or videos that you can find online, the formula to figure out this vector value function always starts with your initial force or the magnitude. And that would actually be this particular rate at which the water is coming out at 80 feet per second. We would then multiply that by the cosine of the angle 45 degrees, then times our time t. I'm going to go ahead and put the t in here first just to allow the interpretation of this to be a little clearer. And then the 45-degree angle, we use cosine when we kind of join it with the I component. We'll use sine here in a moment when we use our J component. And that particular J component starts the same way. We use our force of 80 times T. Like I said, we use the 45-degree angle for sine. And then we tag onto that our gravitational component, the negative 16T squared. And all that would be multiplied by J. Now, technically, we would want to put the initial height in this particular situation, but I'm going to go ahead and simplify that and just allow us to use 0. Although that's probably not likely. The fire hose is probably going to be at least waist high, but we're just going to treat that particular distance from the ground as somewhat negligible here. So we got an equation, or we got an expression here for the vector value function. What are we going to do with it? Well, we just got to think about this a little intuitively. We're trying to find the maximum height. All right, this is a calculus problem taken in a calculus class. If you think about finding the maximum of a function, we would always rely on the derivative of that function and use the critical numbers and analyze it accordingly. So we're not going to really do anything differently here. It's just that because we deal with the height as our targeted maximum, we only really need to focus on the y of t, the component that's with the j. So you're really finding the maximum y of t in this particular case. And that's the only derivative that really needs to be addressed. So we're going to go ahead and do that. We're going to take that derivative, and I'm just going to call that y prime of t. That's kind of the reason why I decided to label this position vector like I did at the beginning. So the derivative here would be, well, the sine of 45 degrees along with this 80 are nothing more than just constants. So we could kind of put those together. 80 times the sine of 45 degrees, because when we take the derivative of that constant times t, all we're going to be left with is that constant. And then, of course, the derivative of negative 16t squared is negative 32 times t. Now, we want to set this equal to 0 because we know that that's when we would reach that maximum height, when the rate of change of that height is going to be 0. Basically, we shoot the water up and then it comes straight down. So we're going to solve this for t. And once we say subtract 80 sine of 45 degrees over to the right side, of course it would have a negative in front, I suppose, and then divide by negative 32, we'll see that one of the first things that's going to happen is those negative signs would cancel. And I'm going to go ahead and use a calculator to solve this. I know that you could handle this knowing that the sine of 45 isn't too terribly bad, square root of 2 over 2. But because we're going to probably want to relate to this, to the real world, we'll most likely will use decimal approximations. So we'll go to the calculator. I'm going to use the TI Nspire here, and I'll just simply enter that particular result that I had, 80 times the sine of 45. Make sure that because our calculator is in radian mode here, if you're using a calculator also in radian mode, that you put some kind of a degree symbol. And then I'll divide that by 32. And I know that if I'm using the TI Nspire here, if I put a decimal in my input, that'll produce a decimal output. So I'm going to say 1.76777. I'm going to go ahead and keep all of those decimal places. And that would be the time, 1.7677, that would be the time that this water reaches its maximum height. It takes 1.7 seconds for that to happen, but that does not answer the question, what is that actual maximum height? So in order to do that, we would just simply take our y expression and evaluate it at 1.7677. Now, it's likely that you probably might sit there and think, well, wait a minute, how do we know that this particular t value is going to produce that maximum? Yeah, that's a very good point. We probably ought to investigate how we know that's going to happen. One of the quickest ways to do that is probably by using the second derivative test and just running through a derivative one more time of this expression, seeing that you're going to get negative 32 as a constant. And no matter what value of t that we were to insert into this expression, y double prime is always going to be negative for all values of t. So that pretty much guarantees that this critical number that we got is going to end up producing the maximum. So if you need help with that, just review the second derivative test from AB. So getting back to the situation here, we just need to plug this 1.7677 into this expression right there. So we'll go to the Nspire, and in the event that I want to use that particular expression, maybe more so in this problem, I'm going to go ahead and define it. I'm going to call, oops, not that, I want to control template, there we go, colon equal, I'm going to define the y of t. It should be 80 times t times the sine of 45 degrees minus 16t squared. Suppose since I'm using this calculator to evaluate this, since this is a CAS calculator, I probably could have used it to take the derivative, but it was a fairly easy derivative to take nonetheless. So what we'll do now is we'll evaluate that particular expression, y, and I'll just go up and grab that particular value and I can just hit enter. It's going to give me a little bit more decimal accuracy. That's not a bad thing. And I end up with, wow, who'd have thought, a pretty nice rounded, integer whole number, 50. And that's exactly what's our answer is going to be. We're going to be able to reach a height of 50 feet with that fire hose. So we know that if our building is more than, say, 5 stories, that we could have a problem and we might need to get the ladder truck out so that we can gain a little bit more height off the ground. All right, let's now take a look at part B here. Let's see if I've got enough room to do part B. So part B asks or says if the building does completely burn down and the firemen are still dousing, water, the wreckage with water to take care of any, remaining cinders and so forth. How far into the wreckage can we reach? So basically what we're looking at now is how much we can extend this x of t, since x of t is the horizontal distance. Now, if we think about what we're doing here, in order for us to reach that distance, let's say that this is, let's redraw this a little bit differently. Let's put the building over here. There's all the rubble, and we'll put the ground right here. Yeah, I could get really creative with this. How about we put like some smoke, coming from the ashes and so forth. Okay, that's enough. And then we've got the fire over here, the fire hose over here, and it's shooting, as much water as it can deep into this wreckage. And we know that this distance from the beginning of the wreckage is going to be 25 feet, of course. But the question is, how far into the wreckage, how far into this wreckage can the water reach? Well, if you think about it, once our water reaches its intended target, we know something very, very obvious about the y of t expression. And that is that quantity is equal to 0. So all that we need to do in this situation is to take that y of t expression, which was 80t sine of 45 degrees minus 16t squared, and we need to set that equal to 0. And what that will give us is the amount of time it takes for that water to leave the hose and reach that particular wreckage. Once we find that value, t, then we can just use it into our x of t equation and figure out the distance that we have to travel. Now, this equation here is not trivial. It's a little tricky to solve because it is a quadratic. It likely, may or may not lend itself very well to factoring. It turns out that it actually does. When you factor this, you bring a t out in front, and you would end up getting a t equals 0 as one of the answer choices. I have a CAS calculator that would handle this wonderfully. I mean, it's pretty much going to take care of this with no problem at all, because I can just type in, let's solve this y of t expression up here, set equal to 0 for t, and I can make sure I have a decimal in the input, and I'll get nice decimal output. And there you see the t equals 0 and t equals 3.535. But because I know that my audience might not have a CAS calculator, or my very own students, you might come across this problem. I would say on the non-calculator part of the test, but that's likely that won't be the case because of the t that you saw in part A. But I want to still go ahead and show how you could easily solve this by doing some factoring. If you want to factor out something in addition to the 80, something in addition to the t, you certainly were welcome to do that. One thing that I would probably do before I begin anything is to take care of this sine of 45 degrees, because he's just kind of getting in the way. So we'll evaluate that as our square root of 2 over 2. And then, it's just me, but I'm going to go ahead and multiply through everything by a negative and rearrange the terms a little bit. And in addition, I can cancel a little bit or reduce an 80 over 2. Hopefully you guys follow that step okay. Multiplying both sides by a negative. And then at this stage, I can factor out a 4 or an 8 along with a t, and that would leave me with 2t minus 5 square root of 2 is equivalent to 0. Well, when I set the 8t equal to 0, it's pretty clear that t equals 0 is going to be a result. If I were to set this other expression equal to 0, 5 root 2 over 2 is what I get, and it just so happens that that particular value, if I return to the calculator and enter 5 times the square root of 2 over 2 with some decimal input, does give me a very familiar result. So for the purpose of this problem, let's go ahead and use the decimal value because we can relate to it just a little bit better. So what we know is that this is going to happen. We are going to reach this particular wreckage at about 3.535. Let me double check any other decimal places. 3.53553, we'll call it, seconds. But that doesn't answer the question. That's not how far into the wreckage we're going to be. So what we're going to have to do is take this x of t expression, which I'm kind of highlighting over here, and we're going to have to plug our value of t in for that particular expression. Now, I don't have that thing defined in my calculator, but no worries. I'm only going to use it one time. So let's just go ahead and enter it. 80 times that value of t, and that value of t is just this guy with even more accuracy, multiplied by the cosine of 45. And because I have a decimal value in my input, I'm certainly going to get a decimal output. And you know, it's kind of surprising. You get this nice number of 200. It's, again, you're going to find out that if we would have used the actual square root values instead of these decimals, the algebra would have been very, very manageable. But it was really important to me that we could kind of relate to that time a little bit, because I thought that was interesting that it takes 3.5 seconds for the water to reach that particular place. So 200 would end up being the distance, but is that our answer? The 200 is actually this entire distance from the beginning of the hose to the wreckage. We are asked how far into the wreckage. So you're going to have to subtract that 200 and the 25, and you actually get 175. And you can tell that my picture is not anywhere near drawn to scale, of course. But that's important to see that we do need to make sure that subtraction takes place. So we can just simply finish up the problem by saying that the water reaches, let's see if I can actually write somewhat legibly here, that the water reaches 175 feet into the wreckage. And that takes care of it. That answers both parts of the question. So anyhow, on my YouTube channel, you'll find a lot of other videos that deal with vector value functions and the motion that is sort of attached to them. Some of them are kind of interesting, like this one. Anyhow, I hope this helps, and I'll see you next time.